So how did the homework go for shunting yard? Scale of 1 to 10. 10 being impossible, 1 being easy. 6? What about over here? Did you do it? Still in Chicago?
One it says can't execute the method OnClick. Maybe the one you told me that would add method manually. It doesn't detect the method.
The OnClick method?
Yeah.
Well, I mean that's just interface stuff. It has nothing to do with shunting yard. That's just Android working.
No, that's what else is the could not execute method for Android OnClick.
Right. So that's going to be. Did I start this? Did I start one for shunting yard yet? I did. All right, that was your starting point. So if I come in here, actually, let's. And we'll choose the normal API level. We'll go empty. Say main activity. All right, well, so our starting point needs to be reading, well, being able to type in the formula that we want to solve, right? So take this one step at a time. So go to our activity main. Ooh, that is big. I'll go ahead and get rid of the hello world thing there. I'm going to go ahead and throw in a vertical linear layout in here. And then I'm going to throw a text box there at the top. And we're going to call this guy input ET. It's going to be our input edit text, that dude. And we'll give it a hint. Will be enter formula, something like that. We'll take the current text that's in there out. And person's name should be fine. Is there like a mathy one? I will just leave it as person's name. That keyword should be fine. Okay, so that guy's going to look like that. Then we're going to go ahead and give ourselves a button to read the stuff in from that guy. And then we'll show him how to do the OnClick thing. So we'll go to widgets, we'll go to button, toss the button in there. Say click me, something like that. And then for right now, let me just put a text view here. We'll call this output TV. Leave it blank initially. And just to get everything working, we'll make it so when we click this button, whatever's in here gets put here. Just proving our buttons and all that stuff are working together. You should do this for all of your applications to make sure you're not spending all this time typing in logic when the function's not getting called correctly. All right, so we need to give ourselves programmatic access to this. It's called input ET. to read in from there. We need to give ourselves programmatic access to this called output TV to write out to there. And then we need to give ourselves a function that this guy can call with his OnClick. So we'll go to main activity. We'll create a private edit text input et and a private text view output TV, and then we'll go ahead and connect those guys. So we'll say this dot input et is equal to the edit text version of this dot find view by id r dot id dot input et. This dot output TV is equal to the text view version of this dot find view by id r dot id dot output TV. All right, so now we have programmatic access to both of those guys. Now we need to give ourselves a function to put in for the OnClick. So this guy will be public void, and we'll call this OnClick me button pressed. This guy's going to take a view v as a parameter. Now, what is this view? Remind me, what does this guy represent, this view that gets passed in here? Give me 1 second, I gotta let. So, what is this guy for? What's the purpose of that view? Do we necessarily know anything about text views here? Who are we going to connect this to? We're going to put this on the OnClick of some button probably, right? All right. Now, there are some other OnClicks. There's other widgets that can have OnClicks, but for us, the only one we know about are buttons. This guy is the view, or in our case, the button that called this function. So I could have two separate buttons that both have their OnClick event be this one function. So I might be interested in whether the view was button 1 or the view was button 2. Who called me? I might do different things depending on which button called me. Make sense? So this is a way for a view to, well, this is a way for this function to know what view actually called upon him. And it also has to have a view in here in order for our other side to see it. So we'll go back out and hook that in. I come in here, I hit my click me button, and I go to OnClick. There's that function. That function would not show up there unless we took a view as a parameter. That's the format for that function. So now when I click this button will send himself in as a parameter, saying I was the one that clicked it. So the view here will be the button that clicked it. We don't have to use it, but if we were interested in knowing who clicked, who called me, that's what that guy's for. Make sense? So we'll go ahead and we're going to read in from input et. So and output to output TV. So we'll say output this dot output TV dot set text equal to this dot input et dot get text. Just proving that all of our stuff is gluing together. All right, makes sense how this works? So let's go try this. Let's do it this way, and I'm going to show you an example. Pretty clear. So let's look at it. I must be doing a poor job of explaining it, so I'll just show it so it'll make sense. Let me do it. Okay, so we'll go ahead and just type an LOL here. I'll say click me, and then there's LOL there. Button works. Make sense? So for your error, make sure that your function looks something like this. It has to be void. You can call it whatever you want, but it has to take a view v as a parameter. If it doesn't have those things, your button's not going to be able to have it as an OnClick. Okay, so now what I'm going to do out here just to show this, we'll actually end up taking the button away, but just for the time being, I'm going to copy my button, just give myself a second one. All right, and we're going to call this guy button 1. We're going to call this guy button 2. We lucked out. Pre-named it button 2. So here's button 1, button 2. And then down here, we want to know which button was called. So I'm going to give myself programmatic access to these buttons up here. Notice that both of these guys, because I copied them, already have the correct OnClick function. So this button and this button both call that single one function. So when I call this guy, he calls that function passing himself in. When I click this guy, he calls that function passing himself in. Two different buttons. Now I'm going to go ahead and give myself programmatic access to the two buttons so that I can ask the question. If it was button 1, put into my text view, button 1 clicked me. If it was button 2, put in my text view, button 2 clicked me. I'll go back in here and I'll say private button 1. Private button 2. This dot button 1 is equal to the button version of this dot find view by ID r dot ID dot button 1. This dot button 2 is equal to the button version of this dot find view by ID r dot ID dot button 2. And then down here, rather than just passing this stuff right through, we're going to ask a question. If v is equal to this dot button 1, if the generic view that was passed in here is the same as the view associated with my button, because anything we see on the screen is a view. It's a plain Jane view. But we know that we have this function hooked up to two buttons, the OnClick for two different buttons. So even though this guy is a little container built for holding any kind of view, we know that the only possible kinds of views that will be in there, in our case, are buttons. So I'm asking, is the view that this guy points to the same as the view this guy points to? If it is, this dot output TV dot set text button 1 was clicked. Else if v is equal to this dot button 2, this dot output TV dot set text equal to button 2 was clicked. All right, so we're asking a question. We want to know who called this function. If the guy who called me was the first button, print out, we'll put in the output TV, button 1 was clicked. If the guy who called me was button 2, put in there button 2 was clicked. There's button 1 clicked, there's button 2 clicked. So when I click this guy, he passes into that function a pointer to himself. And that gets stored inside that variable called v. When this guy gets clicked, he passes into that function a pointer to himself. And that pointer gets stored inside that variable v. So we're able to ask questions, who called me? Make sense, the purpose of that?
Yeah. Yeah, I was just thinking about it the other way. We're gonna have to list functions and pattern view V and then maybe use Z. And then use that for two variables.
Well, the functions for OnClick cannot take in two variables. It has to be a function that, I mean, the only two things that can change in that line I have highlighted there is the name of the function, you can call that whatever you want, and this variable name. You can call the variable name whatever you want, but it must be a view. Okay? And this stuff translates over to iOS development as well. So this, even though we're seeing it here in Android, if we were looking at iOS development, this Swift function might look something like IB action on click me button pressed UI view sender, something like that. So instead of it being a view, it's a UI view on the Mac side. And instead of the default variable name being V, it's sender, who called me, who sent this message. And IB action is the thing that flags it as being, it exposes it to the interface builder side of things on iOS, just like us rating this function in this particular format exposes it out here, so it's in this dropdown for OnClick. So this isn't some proprietary special Android thing. It's just how Android implements MVC. What's MVC? Okay, and what is that guy? What's the idea of MVC? What's the purpose? Yeah, it says that it's a good idea that we keep our logic in one place, our interface in another place, and maybe our data in another place. So don't put all the stuff in one place where things are going to start getting disorganized. But then we need to have some sort of magic that connects those guys back together. Make sense? All right, so this is an example of MVC for this guy. All right, so what I'm going to do is I'm going to go ahead and I'm going to take out this second button, because we don't really need that one at first. And I want to go ahead and I want to tokenize my individual pieces. Because we might have something in our formula, for instance, I'm just going to put some text in here. So we might have like 123 plus 8 divided by 2 times 5, something like that. So for our homework, it was just supposed to support plus, minus, times, divide. And did I say you had to do parentheses or no parentheses? No parentheses. Okay, so just those 4 operators, right? Okay, fair enough. All right, so this has most of them in there. So we need to get the individual pieces here. So we should have 123, we should have plus, we should have 8, we should have slash, we should have 2, we should have times, we should have 5. We need to get those tokens. All right. So how did you go about getting the tokens? What approach did you use? So I'm going to read this in as a string, right? So when I read that guy in as a string, he's just going to get spit back out as a string. No longer need button 2. Actually, I don't need either of my buttons. So I'm not going to programmatically need access to that button anymore. Did I hard code a formula in there? Whatever, good enough. All right, so right now it's giving me my stuff like that. I need these as individual elements so I can put them into a queue, right? So what approach did you use to get individual elements out of those strings? This is kind of the first problem we had to solve for our homework. How did you do it? I'm actually asking you. So this was the first part of this. So how did you do this part? Okay, well,
Take a string, take each element, push it into a list.
okay, well, how did you get the elements?
Created another text view to start and rearrange it.
Okay. How did you pull this 123 out?
From string.
Yeah. So if I have a string that looks like this, and I need to pull the 123 out of it, how do I do that? Because we're entering our inputs like this, right? But ultimately, I need to create an input queue that has a 123 in it, a plus in it, a 23 in it, a divide, and then a 5. I need those as individual pieces. Yet I have them in one giant string right now. So how do I get those individual pieces?
At the end, you were asking about how you got each part of the equation, so I used spaces as stoppers.
Okay. So you said that you assumed that there was going to be a space in between each thing. Okay, fair enough. That's a reasonable enough assumption. All right, so you assumed that there would be spaces. So then that means that the first guy was up to, but not including where you found the first space. Second guy was up to, but not including where you found the first space, but after the first guy. Okay, so how did you go about doing that based on spaces?
I took all of them and identified the operators. So I said either was plus, minus.
Well, even before that, if I have something that looks like this, 123 space plus space 21 space divide space 5. I want to know, how did I get the 123, the plus, the 21, the slash, and the 5 as separate elements? Now you're saying you assume there was a space in between each of them, right? So that means I can start walking through here, and as soon as I hit a space, I know I've captured something. All right, and you're going to put that somewhere. Then you're going to skip past that space. You're going to start building up something else. Is this how you did it, or did you use a different technique for getting these things? How did you get these individual components? Because you're going to need these individual components in order to solve this problem. So we can't even start doing shunting yard until we have this string broken into 5 different pieces that we can load into a queue. Correct?
I was keeping track of where, like, your progress so far.
Okay.
So using index log.
All right, so you're going to start off at bucket 0 and start building up stuff. So we maybe will say we need to go through every element in this string.
And then keep track of your progress.
Okay, so we'll say string, let's call this guy input, is equal to this dot input et dot get text dot toString. So that'll be the string version of that guy. And then maybe we're going to have a string curval that starts off as the empty string. And a for loop for int I is equal to 0, I is less than input dot length I plus plus, because we know we're going to have to go through every element in the string, right? All right, we have to go through every element in the string. And now, as long as I'm not looking at a space, if I'm not looking at a space yet, I want to build up my next character. So if it was something like 123 plus 32 minus 4 times 5, like that, is this a space? No, collect it. Is that a space? No, collect it. Is that a space? No, collect it. Is this a space? Yes. So I'm done collecting my token. And then I need to put it somewhere, right? And for this, we're going to put it inside of a linked list, a queue, a place we need to store it, right? Okay. So we're going to need access to a, I'm going to build simple models of these just for good practice. So I'll go into my project here, under app, under Java. I'm going to right click and we're going to create a Java class here called queue. All right, and a queue is a first in, first out. It's a line, right? So this guy is going to hold strings. So we're also going to need a node. And we're going to have a private string payload and a private node next node, then public node payload. This dot payload is equal to payload. This dot next node is equal to null. And then we need to generate getters and setters for our next node. And we need to generate a getter for our payload. All right, pretty much the same node we've written before. So you can have taken it from your previous assignment. All right, so that's what our node's going to look like. And these are the same nodes that we can store inside of our queues. We can store these guys inside of our stacks. All the same stuff, right? Okay, so here's my queue. Now, what's a queue? A queue is a when we add something to a queue, we get in line at McDonald's. We get in the end of the line. When it's our turn, we get out of the front of the line. So we add end, remove front. Make sense? That's what a queue is. So we're going to have a private node head. We'll keep track of the front of the line. Now, just for convenience sake here, I'm going to also keep track of the end of the line. That'll make it very easy to put things in and out of the queue. Because this is going to keep us from having to start at the head, walk all the way to the end, and then put something there. Okay? So I'll keep track of the beginning and the end. And we'll have our constructor for our queue. So we'll say this dot head is equal to null. This dot tail is equal to null. Okay, and then we need to write some functions for adding to the end and write from some functions for removing from the front. So we'll say public void AddEnd, and this guy is going to take in a string payload. Okay, and we're going to be creating a node regardless. So we're going to say node n is equal to new node, passing it that payload. So we have a brand new node now. Now, if head is equal to null, if we have the empty list effectively, so if this dot head is equal to null, then we'll say this dot head is equal to n. This dot tail is also equal to n. The head and the tail will both point to the one element since we had an empty queue before that. Otherwise, there must be something in here. And since I'm adding to the end, what am I going to do? I'm going to make tail point to this guy. And then, well, I'm going to make tail's next node point to this guy and then make tail point to my new guy. So I'll say tail dot set next node to n. So whatever tail currently points to, I'm going to tell that guy to set his next node to n. Then I'm going to say this dot tail is equal to n. No. If we draw the picture there, this is let's say this is our current list. This is the new guy I'm adding. This is head, which points here to the front. This is tail, which points here at the end. So when I add end, I'm going to take this guy. And so just to, so this guy's next node points here. This guy's next node points here. This guy's next node currently is null. So the very first thing I'm going to do is I'm going to say tail, which is this guy, set your next node to the new guy. Then tail will point to the new end of the list. Make sense? Draw pictures with these guys. Okay. So back in here, so this should just be AddEnd. Public node remove front. We're going to say node to remove is equal to this dot head. If this dot head is not equal to null, if I actually have stuff in my list, then I'm going to say this dot head dot set next node to null. So I'll disconnect that current. Actually, I don't want to do it that way. Do it a different way. So since I'm disconnecting this first guy, when I remove the front, I'm first giving myself a pointer to this guy. So this is my node to remove. So I'm going to make this guy point to the same thing head points to. Then I'm going to make head point here. So head will point to his own next node. So this dot head is equal to this dot head dot get next node. So that's this part. I said it, but we'll do it here. But before I do that, I need to say n is equal to this dot head. So I need to make n point to the same thing that, and it's not n, it's node to remove. Node to remove is equal to this dot head. That's this thing. So this guy points to the same thing that head used to point to. Next line, we say head is equal to head's next node. That does that. The last thing I want to do is I actually want to finish disconnecting this guy. So we'll set node to remove dot set next node to null. Like that. And then we'll go ahead and, now we do need to ask an additional question here. We need to say if this dot head is equal to this dot tail, then we'll say this dot tail gets reset to null. If I have the one list and I'm removing stuff, I need to reset my head and my tail. So if I'm removing from the front, if head and tail are the same, the node I'm going to remove is going to be head. Head's next node will be equal to null already, naturally. I'll disconnect node to remove, but then I need to make sure that before I've changed head at all, if it happened to be the same thing as tail, meaning we had a list that only had one element in it, we'll just go ahead and naturally reset tail to null. We have nothing in this queue. And lastly, after we've done that, we will return node to remove. So that gets it out of the front of the line. This puts it into the end of the line. Make sense? So now we need to go into our main activity. I need to give myself a queue to put this stuff in. So I'll say queue is equal to new queue. Actually, let's call this same thing as shunting yard uses it. So we'll call it input queue. All right, so we're going to build up our current value. And then as soon as we get to the space, if we're assuming there's spaces between them, we'll go ahead and add to the end of our queue the value we've built up, reset the value, and keep going. So each time through here, we're going to ask the question, if input.char@, the current value I, if that guy is equal to a space, that means I've hit a space. And what do I want to do when I hit a space? I want to say input queue dot AddEnd curval, then curval gets reset to the empty string. Else, if I'm not looking at a space, I'm going to say curval is equal to whatever curval currently equals concatenated with input.char@I. When I hit a space, add the curval I've been building up, zero it out. So not a space, not a space, not a space. Curval currently is 123. Now I hit a space. What do? I take my 123, I add it to my queue. Then set curval back equal to the empty string. I've skipped past a space. Is that a space? No. Add it to curval, so it's a plus sign. Now I hit a space. Curval was plus. What do I do with it? Add it to my queue. Set curval back to the equals, the empty string. Now I'm here. Not a space, not a space. That's curval. Add it to my queue. Not a space. That's curval. Add it to my queue. Not a space. That's curval. Add it to my queue. Not a space. That's curval. Add it to my queue. Not a space. That's curval. Add it to my queue. Now, when I exit this for loop, though, my very last, assuming I don't have spaces there at the end, my very last curval is currently stuck in there. So I do need to ask one extra little question down here after the for loop is done. If curval.length is greater than 0. If there's something in there, go ahead and add it to the end of my queue. It's kind of like you have one last thing stuck to your hand. Right? You got to put it in the end of the queue. All right, so far so good. All right, so another important thing for our self-evaluation stuff. So far, nothing we've written has been all that difficult, but it would have been difficult for you to write it, right? What's the real skill that you're lacking right now? Not the programming skill. It's the skill of breaking things down to the little tiny problems. When you sit in front of these homework assignments, you know, you're scared to death and you think the problem is this big. And the big problem is that big. But the first part of that problem is this big. The next part is that big. The next part is that big. So on and so forth. So if you tackled one little tiny problem per day, for example, you'd ultimately have a solution to a much bigger problem. That's what I can't get you to practice that without giving you big problems. Does that make sense? Same thing's going to translate even if you don't become a professional programmer and instead you're, solving problems in the IT industry. The same thing's going to happen. If you're running a network for a college campus like this, that's a big, 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 big job with lots and lots and lots of different moving parts. There's no way for you to conceive upon the entire thing. You're going to have to say, okay, I need to understand what I'm trying to do at this broad level. Then you got to say, where do I start? I'm going to start right here. What's that micro problem I have to solve? Then what's the next problem I have to solve? And the next problem. And all your decisions happen in context of the big idea, the big problem you're trying to solve. But understand how this is no different? So this level of critical thinking is what we need to practice, because you need to be able to take big problems and break them down into little problems. And we're all really, really good at that. We just forgot. When I first went in 535, usually the first week I talk about what the problem with beginning programmers is that we're, as human beings, we're so good at solving problems, we've forgotten how to solve them. I usually ask the question, like, how many of you fell down on your way to class today or bumped into a wall or something like that? Most of us text while we're walking. It's not even worth our time. But do you think walking from the parking lot to this classroom is a trivial task? You have to keep yourself balanced. You've got to put one foot in front of the other. There's all these muscles that are contracting and firing and all these things that are happening. More things that we could even, thousands and thousands and thousands of little things are happening. It's something that's just so much more complex than this, right? But which feels more complex to us? Stupid homework assignment, right? We're already good at walking into the building. We don't even think about walking into the building. We already solved that problem when we were 1. Okay. We couldn't feed ourselves, but we learned how to walk. Kind of get where I'm going with this? We need to get better at conceiving large problems and breaking them down into small pieces. And I can't get you to do that unless I give you big problems. I don't really need you to solve such a huge problem, but I need the problem to be big enough that you're forced to solve small problems. Okay? So I just wanted you to understand kind of the mentality where I'm coming from with these things. All right, so when I'm done with this, my queue should have all this stuff in it, right? So now, just for testing's sake, let's just go ahead real quick and teach our queue how to display himself, how to get some text out of himself. So I'm going to say public string convert to string. And this guy's going to walk the, you know what? I actually don't want to build this into the queue. That's going to make life. I'm just going to prove it to myself along the way. So this will just match up to my queue. So what I'm going to do is I'm going to create a string called answer, start that off as the empty string. Right before I turn curval into the empty string, I'm going to say answer is equal to answer concatenated with curval concatenated with maybe a space and like an arrow looking thing like that, just to show us the separation. Okay, so this should be 123 followed by an arrow, plus followed by an arrow, 32 followed by an arrow, minus followed by an arrow, 4 followed by an arrow, star followed by an arrow, and 5 followed by an arrow. Is what should end up in there. And then down here, I need to do the same thing. So I'll say answer is equal to answer concatenated with curval. In this case, actually, it won't have a final arrow, so it'll look correct. But this will at least show us that we broke it down into the right pieces. We got the correct chunks along the way. Okay? And then at the end here, rather than telling my queue to convert itself into a string, answer is kind of showing me I got the individual pieces. So I'll just say this dot output TV dot set text equal to answer. Just proving that I got everything. Let's go ahead and run this. I'm going to steal that guy. I can't paste in there. Well, that's upsetting. 123 plus 8 minus 24 times 117. There's my 123, followed by an arrow, followed by plus, followed by an arrow, followed by 8, followed by an arrow, followed by a minus, followed by an arrow, followed by a 24, followed by an arrow, followed by times, followed by an arrow, followed by 117. Got my pieces? Okay, got my individual pieces. Take the jacket off now, we're getting warmed up. Okay, so those are our individual pieces that we've proven that we've gotten them into the queue. So what do I do with it at this point? Well, now we got to bring up our shunting yard algorithm. So this is what we've built, this piece right here. Okay, so what do we do? Well, we're going to need an output queue, and we're going to need an operator stack. So I'm going to go ahead and build myself a quick stack as well. Okay, now you made a comment earlier. You said stacks are hard. Tell me why stacks are hard. So is it actually that stacks are hard? It's that we suck at breaking big problems into small pieces? Yeah. Now, do all of us at least recognize that weakness at this point? It's important. We all need to recognize that we suck breaking hard problems into small pieces. Because that's how we're going to measure the success in here, right? Told you last class that I'm going to work the heck out of you. And then at the end, you're going to get, as long as you go on the journey. Don't skip class to stay in Chicago. You know you had a quiz last week, right? You know we have a quiz every week, right? Yeah, so that'll be your drop, but probably don't do that again. It's kind of the punchline. So as long as you put in the effort, do your, work on your homework. I know the homework's going to be hard. I wouldn't give it to you if I thought it was easy. I want to feel the experience. I want to feel you guys going through this. And in the end, you're going to get a grade that's way better than you probably deserve numerically. All right? Go on the voyage with me here. And on the other end, you'll come out better, stronger, not in Chicago. he's going to get picked on all class today. All right. So, yeah, so we're all recognizing that we need to default to break problems down into tiny pieces every single time. Okay, so I'm going to need to write a stack here real quick. When I say real quick, we think in our head, like, oh, isn't a stack data structure hard? It's actually the easiest one to write. Add front, remove front. It's trivial. That's the easiest of our data structures to write. I mean, Q wasn't too bad, right? That's an entire Q data structure. If you want to be official, it's actually not called AddEnd and remove front. This is called NQ and DQ. But that always makes me think about ice cream, so I don't call it that. I know, we love ice cream, don't we? All right, so let's go write our stack. And we kind of wrote one of these last class for the Towers of Hanoi thing, but let's write it again real quick. It's good practice. Simple, right? Good thing is we already have nodes we can put in our stack, so we don't need anything special there. So stack, we're going to have a private node. I'm going to go ahead and call it top in here instead of head. Okay, because technically it's we always point to the top of the stack. But these are just variable names. Call them what you want. Whatever makes the most sense to you. All right. And then we're going to have our public stack constructor. That'll say this dot top is equal to null. All right. Then we're going to go ahead and we're going to have our push, also known as add front. Isn't that what push is? Okay. So we're going to say public void push. Because of the way we're going to use our stack here, I made my queue such that we're going to be removing from this queue and it comes out of the queue as a node. So I'm not going to, rather than taking a payload here, I'm going to kind of build it for the solution we're going to be writing. So since my queue gives me nodes, I'm then going to put those nodes back into another queue or into a stack. All right. Now, we're also going to need a version of AddEnd that can take in a node. So what I'll do here actually is I'm going to say public void AddEnd node n. And we'll take all of this code here. We'll pop it in there. And then this guy, we'll just call this dot AddEnd, passing it the node. So I have an AddEnd function that takes in a node n and does all the logic we did before. Or I have one that takes in a string. And what does he do? He builds a node and then passes it to his other version of AddEnd. Make sense? Little convenience method. Now we can build our queue using our strings because that's what we were reading from our original input. But then we can also build our queue using pre-built nodes, which we're going to need in our output queue when we add stuff to the end here. Right? Because when I remove something from my input queue, I'm going to decide whether to push that node onto my op stack or to push that node or to add that node to the end of my output queue. Make sense? In any case, what I'm working with over here is a node. That's the choice that we made. Okay, so over here in our stack, our push is going to take in a node as a parameter. And what's this guy going to do? Well, he's going to put it on the top of the stack. So we're going to ask the question if this dot top is equal to null. If I already have the empty stack, then we'll just say this dot top is equal to n. Else, there's already stuff in the stack. So what will I do? I'll say n dot set next node to whatever this dot top currently points to. And then we'll say this dot top points to n. So what did I do there? I added to the front. This is top. Let's say this was the guy I wanted to add. Top is currently pointing here. First thing I do is I make the new guy n point to the same place that top points to. That's that line. N dot set next node to this dot top. So n's next node points to the same thing that top points to. Then what do? I make top point to the new top. Top points to n. Make sense? You're going to want to draw pictures for these for a while. And even on very complex, I mean, I can pretty much do the linear data structures in my head for the ends. But when you start, we haven't done anything in the middle where, like, you insert something in the middle where you have, you're disconnecting this wire. Okay, I'm going to make this guy point here, and then this guy point here, and this guy point back up here. Just draw pictures, or otherwise you'll drive yourself nuts. All right. So that will add something to the front. Public void pop. And actually, I'm sorry, it's not void. This guy's going to return a node. This guy is going to remove from the top. So we're going to go say node to remove is equal to this dot top. So we'll keep track of the top of the list. Then we'll ask if this dot top not equal to null. If we have something else there, then we're going to say node to remove dot set next node to null to fully disconnect that guy. Then we'll say this dot top is equal to this dot top dot get next node. So top will point to the next guy in the list. Return node to remove. It should look identical, well, except for the couple of different names, to remove front from our queue. Because that's what we're doing. We're removing from the front. Here's remove front in our queue. We had to keep track of a tail in queue. That's what this. So it's identical except for this piece there. Why am I doing? Yeah, this is actually redundant. We're doing it twice. So you don't actually need this line there. Now it should look identical. It wasn't broken before. We were just doing the same move twice. We set node to remove equal to this dot head 2 times. We just it's really made sure it's stuck on there. All right. So go back into our stack. This is pop. Now what does peek do? Okay, so it shows us the top of the stack, but doesn't remove it. All right, so what I'm going to actually do here is I'm going to say, we certainly could write something similar to that, but not actually disconnect it. Well, actually write something even easier here. So we're just going to say if, actually we can make it return, so really this guy's just going to return this dot top. If it's empty, return null. That's fine. That's not going to break anything. We'll have to make sure we check on the other side. You know, if somebody gets a null value, you start trying to call stuff on it. That's bad news, but so we're just returning the top. We're not disconnecting it. We're not doing anything special. All right, so that's our stack. Now I'm going to go ahead and give myself a little helper function here that's going to be handy for us. I'm going to say public boolean is empty. And I'll let this guy be able to report to us whether or not he's empty. So this guy should return true if top is equal to null. That means we're out of stuff. And that's going to be handy for us when we need to burn through our operator stack to get rid of that old stuff. All right, so return this dot top. It's equal to null. That's for is empty. Okay, questions about any of this stuff so far? So we got a couple of widgets sitting around, right? We got our queue right here. We plan on using this guy twice. It's going to be our output queue. He's also our input queue. We're already using from our input queue. So if we kind of draw our picture here, what do we currently have? Let's steal this slide. Oh, it's quite interesting. There we go. So I have my input queue here. And I'm gonna have an output queue. So this guy we've already done. Okay, we're gonna have an output queue. And we're gonna have an op stack. So both of these guys need to still be implemented, right? But we've written the data structures for these. So this is the same data structure we used here. The only thing we needed to do is give ourselves an AddEnd that took a node instead of a string. And this is our new stack thing that we just wrote. Okay, now we're going to need one other piece here. We're going to need an op compare. That's going to allow us to know which operators are allowed to go on top of other operators, like what the rules are before we just throw it onto the stack. Make sense? And then we're also going to need process output queue, the thing that takes this guy and ultimately gives us our answer. Okay, so we've written this piece as well as the supporting stuff for this and this. We've also written the supporting stuff for this guy, because this guy, to process it, needs a stack. All right, so let's take about a 10-minute break. We'll come back. we'll get stuff. We're going to feed from our input queue into our op stack, feed from our input queue into our output queue, and get those two guys set up, ultimately getting everything into our output queue. Then we'll write the process output queue. All right, so come back at 6:37.